All right, picking back up. I'm getting tired of listening to my crappy mic, so I've actually ordered a new one from Amazon. I don't know when it's going to get here, and I'm not sure what that means. Does it mean that I don't have to go back and re-record some things, or the audio really blows? I don't know. I'm kind of figuring out where I want to go with this series, and maybe if I want to do a different series and whatnot. It's sort of a segue here, but in the previous video, I had talked about, well, this is going to be the last creative burst. Um, that's probably a load of crap. There's many personal reasons why, but I don't know. It's enjoyable for me, and I'm just gonna keep doing it. And I have my own little corner of YouTube with 100 hours of video about Cheat Engine and assembly and crap like that. When I do get the new mic, I'm gonna probably find a different way to record the stuff as well. I like Cam Studio. I want to support Cam Studio. I've given them this little window has been a fixture in the series, gotten a lot of free publicity, but there's some audio syncing issues. Maybe I'll look into just fixing that with Cam Studio or using some other program. But basically, once I get the new mic, I'm gonna actually sit down and figure out how to do like a proper sort of production, and so that's all I'm gonna say about that. So I like fixing bugs sometimes. I hope you like fixing bugs because that's what we're doing. So let's bring this back up. What is the problem that we were dealing with? The problem that we're dealing with is that we had this big string. Is initially we had this is what we had, and this is what we were using our AOB scan for, and we were getting two results, and more often than not, the one that we wanted was showing up first, but every once in a while it would switch, and we were clobbering the wrong instruction, and there's all kinds of technical reasons as to why it exists, and we're going to get into some of that stuff in this video. But basically, we needed to make this more unique, and what we were doing is essentially just appending a ton of bytes or essentially their instructions, but we were just appending different byte patterns onto what we already had in an attempt to make it unique. And then what we ran into was that some memory addresses had been hard coded, or yeah, we'll just say hard coded, to where it wasn't an offset in memory with a register. It was just some fixed address that would change every time the game started up. We talked about that in the last one. So basically, the central thing we're trying to fix is find a unique way to identify some memory location for removing the point with a byte string. And so we're going to keep moving in that direction. So we're going to close it, close it. I just want to get rid of the changes. So let's open up the game. All right. I also ordered a new mouse too. Not that anyone will notice, but my current mouse, it's a laser mouse, and it's just the lens is scratched and it's crap and it's skipping, and it's really, really, really annoying me. But that's neither here nor there. Right. It's probably this first one. Yep. Okay. So now we're going to find out what writes to this address. Um, let's add 2 and then subtract 1. So we added 3. So the one with 2 is the remove point. So we clicked on that. We're going to show dissembler. So basically, what we're doing is, here's the the byte string that represents this instruction, and it wasn't unique. So then we grabbed this, and then we basically went off on a tangent, and we got all the way up to this point, I want to say, because that's the first sort of hard coded memory location. So it is at E8. You can see that this is what we had last time: 0F, C8, FE, FF. You go over here, it's E8, and then 37, C9, E or FE, FF. You could say to yourself, well, these last two bytes are the same, or at least they're the same this time. is what I would, that would be my response to that, is that it's the same this time. But if you restart the game 1,000 times or shut your computer down, bring it back up, send it to someone else uses a different operating system or something, may not be the same. Whenever you see a memory address um, in an instruction, and it's literally a memory address, not an offset relative to some fixed thing like a register or a variable, whatever you want to say, be very wary. And so we're going to introduce something called wildcards. And basically, what the wildcard, if you have any sort of regular expression, uh, background, or knowledge, say wildcard character. The term wildcard character has the following meanings in computing. A wildcard character can be used to substitute for any other character or characters in a string. Regular expressions, the period, it's not the period, but with the asterisk, it will match any number of characters. That's not, it's similar to the regular expression one, but it just uses different, sort of semantics, if you will. So let's briefly, you could hit F1 and search for wildcard. Let's do that. So you go to value types, binary. It doesn't matter. We're not dealing with, I mean, we are dealing with binary, but what this specific section in the help file is talking about is if you go down here and you select binary, it's talking about how you could use wildcards in there. But the way that Cheat Engine deals with wildcards is sort of universal across the program. We're going to read about it in the context of the binary value type, but it functions the same way in assembler script. So let's see. If you want to search for an array of bits, that's possible too. It even allows wildcard, question mark, and asterisk or star instead of the normal ones and zeros. This allows you to do a search like 1101 question mark 001, which will give the results of all addresses plus bit that have either 1101 0001 or 1101 11001. So what's the difference? That's a whole lot of ones and zeros. The difference is that the question mark can stand for any valid value. So let's see if we can maybe bring that over to the AOB scan here. What is AOB scan relative to AutoAssembler? It'll scan the memory for the given array of bytes. Yeah, we know that. Wildcards are supported. So it doesn't go into a great amount of detail, but what it's telling you is that you can use wildcards in your AOB scan to deal with values that will change from restarting the game, and it will replace all tokens. Yep, yep, yep. Let's see if there's anything else in here. How about that? This is more Lua scripting stuff. Byte value 255 or anything not an integer will be a wildcard. All right. So why do you need this facility? Well, because let's say we wanted to keep adding bytes. At some point we're going to have to just stop adding bytes and find another way to attack this problem and solve the bug. But let's just say that we wanted to keep going and adding bytes. There's no point in doing it right now because these 4 bytes right here, the E8 will be the same because that's the opcode, but then you have 37C9 FEFF. And basically what that is it's this memory address in hex. We could whip out a calculator and maybe demonstrate that, but we're not going to. And let me actually retract what I just said, because this is hex and that is hex, so that was essentially a meaningless thing. What this is these last 4 bytes are this memory address right here encoded as a bit or a byte string. And I'm being sort of purposely vague about it, but what you can see over here, let's go up to where we actually want to inject that. You can see that the move is 8. The first byte is the opcode, so you have 8989. It's not always 1 byte. Could be different, but you can see down here as well that there's another move instruction and it's not 89. Well, you just said move is 89. Yeah, well, this is very tricky stuff, and what I would say is that every instruction, as we talked about, is represented by some byte array or by a series of bytes, and instructions, the opcodes generally do not change. So there is a way where you could get a pen and paper or notepad, the actual program notepad, not a physical notepad, but And you could say, and you could dig out an x86 book or whatever this is based on and say, okay, well, move as an opcode is represented by this series of bits, and then I have an instruction EB, or we have some parameters for the opcode, and then you could convert all this stuff into bits, and then you could convert that into bytes by hand, and this is what you would get. But there's no reason to really deal with that unless you have to, and that's why Cheat Engine, in my opinion, that's why Cheat Engine provides this column, because no one would, I'm not going to say no one, but very few people want to convert this by hand into what the byte string that the processor actually reads is. I'm certainly not going to do that. So what we are just going to say is that opcodes for some constant literal bit pattern, and generally you'll see that it's 888 for the first 4 bits, and then the last 4 bits um, of the byte, it changes. You can see here's a move instruction, it's 89. Here's a move instruction, it's 8b. Here's a move instruction, it's 89. Here's another one, it's 8b. So what is the move opcode? Is it really 1 byte? It's probably a little less, and it's it probably, the parameters bleed over into that first byte, or there's some technical reason as to why it's not here. I don't really care what it is, and I'm not going to bother looking it up. But that's why the same opcode or the same opcodes don't always have the same first byte. It will generally be something similar, but it may not be exact, as demonstrated by these 4 move instructions right here. But that being said, what we're really interested in is demonstrating that this offset relative to EBX shows up over here. It's sort of backwards, if you will, and that's sort of a least significant bit and a most significant bit issue. But E0, E0, and then you have 3 zeros. Just my eyes are killing this. So it bleeds over, and then okay, so there's a couple here, but you can sort of see that there's an offset relative to EBX here. It's 000000 E0. That's generally reflected over here. Here's an offset of 70 relative to EBX. You can see 70 over here, 68. There's 98, but I'm not going to draw any conclusions from that. And again, there's E0 over here, is over here. So the point I'm trying to make here, and perhaps not doing a really good job, is that there are similarities between the parameters that are passed in and the opcodes that are used in an instruction relative to the byte string that represents that instruction. And the reason that this is important is because when you see an instruction like this and there's an actual physical um, hard-coded memory address or static address, whatever the hell you want to say, that there's a fixed memory location, it is going to, the bytes that represent this instruction are using this value to produce this byte string. And so when you restart it and this address changes, the bytes over here will change. And so the reason that wildcards exist in the context of an AOB scan is so that you can sort of skip over this and basically say, I don't care what these last 4 bytes are. They can be anything. I just want to match E8, and then I want to match some byte plus some byte plus some byte plus some byte, and then I want to start E3 C410. The way that you do that is with wildcards. So let's demonstrate that. The last byte that we're going to say is fixed is E8. And then so we have, this is the 4 bytes that we had. We want to skip them. So we're going to do that, and then that, and then that, and then that. You could also use the asterisk, but I like the question marks are just clearer. So what we're, again, just to rehash it real quick, what we're saying to Cheat Engine is scan for this series, or this fixed literal series of bytes. And then when you hit these 4 wildcards, I don't give a shit what the value is. So let's copy this. We will go to AOB, get rid of that, paste it in. Let's get rid of E8. Do we want, no, we'll just go to first scan, see what we get. We get 2 results. And again, what we're saying with these wildcard with the question marks, each one is 4 bits essentially. So 2 wildcards, just like in hexadecimal. 2 is saying, I don't care what this 1 byte is, I don't care what this 1 byte is, I don't care what that 1 byte is, and I don't care what that 1 byte is. And now if you wanted to, which we do, you could just keep going. Say C4, 10, go down to the next one. There's no fixed address or anything over here. So let's do 8B, C8. We'll go to new scan and rescan it. So this is how you deal if you are digging, if you're trying to find a unique byte string or series of bytes, whatever you want to say. You're trying to find a unique byte array, and you're adding or appending bytes on. You're saying, well, here's one instruction, so I'm going to take that series of bytes and then here and then here, and then you're like, oh crap, I have some memory location here. Basically what you're doing is just, well, skip it. Is what you could, that's it. You're just going to skip it. And the way that you do that is with wildcards. I don't care what it is, and then just go down to the next instruction, and then the next one, and then the next one, and then the next one, so on and so forth, as far out as you need to go in order for you to get this down to one hit. All right, so about 15 minutes, almost 16 minutes. We'll keep going here for a little bit. We are pretty far out there with this byte string. It's getting big, but we're going to keep going a little bit. So what do we get? 8BC8. Is there a limit on how big that you can make these things? Not that I know of. I'm sure if you got ridiculous about it and you had 65,000 or something like that, then maybe you might get to a point to where Cheat Engine is just saying, I'm not doing that. Is it going to tell you that it's hit the limit? No, it'll probably be some obscure error. And sort of an issue that I run into is that if you're doing a huge byte string like this, there's no delineation at all. It's just a series of bytes. And when you're adding on bytes you get like 10, 12, 15 instructions in there, it becomes easy to get lost if you're not constantly sitting here staring at this stuff. Um, you know, Especially when you see the same pattern repeated here, and then you see something similar down here. In cases like that, it's easy to get lost. So 8B4598, that's right here. We're going to probably add on until we get down to about maybe here. And if we don't have it, we're going to stop the video, or I'm going to stop the video, and then we'll come back and we'll approach this from a different way. I have a feeling that we're going to have to. And this actually works out because this is the kind of stuff that you're going to do when you try and use AOB scan and write scripts and stuff like that, and you try it on your own time. This is how you're going to do it. So we got 4598, so we're right here. 83EC08 51503900. Oops. B8 D3 4F 5B F4. So I also just something that I like to do when you're making these byte strings and you're adding it on, and just by typing it in, looking up here and I'm typing and whatnot. Um, I try not to add, a shitload of bytes, because if you make one typo, then you got to say, well, F4, where's that? Well, I think it's right here. And then, maybe there's 5B that's here. And you got to sort of, again, it's easy to become lost. So I tend to add it in smaller units, maybe like 5 to 10 bytes at a time, sometimes even less than that. All right, so we are down to one result. I just want to go back here. And so F4 and then 5B and then 4F. Let's find out. So that's where we were. That's where we left off. I want to see what the actual difference is. Or like, I want to find out what byte is indicative of the difference between these two instructions that we're dealing with. So D3, did it just go? Oh yeah, because I'm just an idiot and I typed this address out. So of course it's going to be different because there's a hard-coded memory address right here. And let's, what we're going to go up to. So in the previous video, I had pulled out Notepad and I was typing a whole bunch of crap in, but a much easier way to do it is just to go up to File and go to New. Brings up another memory viewer, and we'll do something like that. When you go to File and New, it'll just start you right at the beginning of the memory associated with whatever process you're hooked to. So go to right click, go to address, and so over here we have the 1356 area that we're looking at. We want to look at 18C2D56A. So 18C2D56A. There you are. Let's make them as close as possible to each other. What are we at now? That's long. It's getting there. So the way that, let me see, this is the instruction. That's the instruction right there. So we're going down. And now it becomes somewhat easier to sort of compare bytes and say, well, here's the instruction here. And I mean, this code is an exact carbon copy. We're gonna stop and then we'll jump back in just 1 second.